So time to wake up. I think I have to take these guys from here. Yeah. So we are running for until what when?
Maybe you have half an hour.
Okay.
Yeah, and then, yeah, but please don't compress.
No, I will not.
Yeah, you can continue. No, that guy brings the tea, otherwise I don't mind. I can tell him to come at 11 o'clock, I think so.
This
Huh?
is easier.
I can do that. I think that would be better. I will ask him to. Or you want 11:15 maybe? 11.
So today we're going to do a little bit of regularity here. We came all the way here. Yeah. So just a few words what you have done so far, since you're fresh now. So we started looking at this problem and we will continue with that. We're assuming U is not negative. We cannot actually allow U to change sign, but that's of no use. If you already are learning at the early stage of the method. Methods are not that much different, technicalities will be a little bit different. The approaches are the same. And this was all in D1. So in D1 we're working with this. And we came down with that U is C11 locally. And the universal north. Second derivatives L infinity are bounded. Say D1 half. They usually depend on the subnorm of this. Depend on the constant. Depend on the subnorm. So constant times subnorm or something like that. Then we came with further information that supremum of U over any pole of radius R with center Z is largely equal U at the point Z plus R squared divided by 2n in this particular case. And when Z is on the free boundary, then it is non-degeneracy. This is called non-degeneracy. The word non-degeneracy is related to this, that U is already C11, so it means that U is less than equal R squared. At the same time, I'm saying that the supremum is not much less than it is approximately like R squared. And we used that to prove, these were used to prove Lebesgue measure is 0. And we prove that Hausdorff measure of the free boundary locally is finite. These were the results so far we have. These are very low regularities. So now today we're going to go a little bit further. And it's also a little bit of different techniques and very recent, fresh techniques. Okay, so let's see what we are going to do. Scaling and blow-ups, we already talked about this a little bit, so we're going to continue with this a little bit. So when you blow up things, scale them and blow it up, then you will have global solutions. And what kind of role they play in regularity theory. And then we talk about good points of the free boundary. So a good point is a point when you don't have a cusp. Of course, free boundaries in this particular case can develop cusps. So we have, if you want to talk about regularity of the free boundary, you have to, at least at this stage, avoid them. So examples can be like this. An example of a cardioid actually you can explicitly write down in dimension 2. So there's a bunch of examples you can actually find them. So the picture is like this. For cardioid, you use positive here and actually you use negative here. There's a region when you use negative actually for the cardioid. But there are examples which look like cardioids but use completely non-negative. Then you use 0 here. So the particular case of cardioid is actually not fitting into the content of our problem. But there are cardioid type regions which really come into play here. So people have been working out this. There is actually a very good description of regularity of the free boundaries in dimension 2. In dimension 2, in a series of papers by Makoto Sakai. Beautiful results from 91 in Acta Mathematica, 91 Acta, plus a few other things, a few other papers after that. And he has actually given a complete description in dimension 2 of the free boundaries, how they look like, which is extremely advanced. Techniques are what's called in French tour de force, so very forcefully really goes into and works out without any tools for complex analysis. And he uses strongly complex analysis. Okay. In high dimension, this is still sort of open problem to classify these. So there are results of 98 of Luis Caffarelli when he says that the singular points, so this is a singular point, in higher dimension you can put them in C1 manifold, in a minus dimensional C1 manifold, or also lower dimensional manifold depending on the character of the points. But that's still not complete classification. There is actually a very recent result, which maybe it's a few weeks old or a month old by Figali and I think Joachim Serra, if I'm not wrong. They have also done very nice classifications of free boundaries. So that's also a new result. Still, it's open question in higher dimension what exactly is the structure of the free boundary. So you don't know that. I mean, when you come here with singularities in higher dimension, a lot of things can happen. You don't know what they look like. Okay, so we don't have to work with the cusp points, so those points we will avoid. So in order to do that, we are going to assume that a free boundary point is sort of some kind of regularity. So that regularity would be, suppose we assume that from outside, if you don't want to allow cusps, you can say, okay, from outside you have a cone. Then cusps are not there. So if you have a free boundary, assume that you have cones like this, then this cusp cannot appear in your free boundary, so you're avoiding them. That's a very simple way of saying it. Another way of saying it is that the volume here is large enough. The volume here in comparison to the radius, this is the radius of a ball. This volume, let's say, is comparable with the volume of the ball. You can also say that.
a little bit better than the cone condition. And then, of course, you can go down with this, and there are very nice, interesting geometric assumptions, which seems to be the borderline. And that was due to Caffarelli. He says that if this cusp is not too sharp, then we're going to get regularity. So he even allows cusps, but he says only if it's not too sharp. And that not too sharp is implicit in the sense that there is a modulus of continuity, and if your cusp is about the sharpness of the cusp is about that modulus of continuity, then you're going to get regularity. We're going to do it, I think we're going to do it a little bit differently. We're going to do it, it's a different interpretation. We're going to do it through monotonic formulas. So we're going to say that if your monotonic function is a new one, it's not the one I told you about yesterday. If that function is not having the large values, it can have possibility of two values actually for homogeneous functions. And if it doesn't have the large value, then you're going to get regularity. So you're going to go into that a little bit. I'm sorry. I feel in
Can I ask one question?
Yes, please.
Regarding that figure that you drew over there about cusp. So, is there an optimal result for like it's about that Caffarelli's result? That
You can not say what is optimal here because it
no,
depends on.
because yesterday you were discussing those cones in a disk yesterday.
I don't recall that.
No, those in complex plane.
Oh, okay, yeah.
So can similar kind of thing be used, because there you can write the angle explicitly and
Yeah,
say
no, you don't have angles here. You don't have cones. The cones do not appear.
It's a cusp, so
It's either a cusp
yeah.
or regular.
Okay.
So free boundaries, in this particular free boundaries, you have either cusps or regular. There are other free boundaries you can have cones, like minimal surfaces in higher dimension. But here you have either cusp or regular point. And we will see soon, maybe today, quite soon maybe, that there are energies, there are integrals that actually you can compute. And you can compute at points where it is regular, in the limit when r goes to 0, that value will give you, let's say, 1, or Cn, or alpha n, I think I'm calling it. And then at points where it's singular, it's going to give you a value 2 alpha n. And they're the only values you can get. And it means that singular points, your functional will have value alpha n, singular points 2 alpha n, at regular points. The reverse. 2 alpha n at singular points, alpha n at regular points. So we're saying alpha n is the lower value. So we say low energy points. So that's the name we give to it. Low energy points are good points. Always if you have, so this is a general conceptual thing which helps with technicalities, is that if you have an energy, always the lowest energy point, this might be a little bit diffused right now, but I will have to come to that and it's very clear. So the lowest energy point in all type of free boundary problems, regularity theory, are the good points. And then there are energy points that are higher, you can hardly classify them. They're much harder. In some cases you can, but generally it's very hard to classify them. And in this particular case, we have two energy levels. One is the lowest one, the other one is the higher one. There's no in middle. In parabolic one of this problem, we actually have a third one in the middle, which we studied. It took us a while to really classify them. If you go to system, you find more, actually, system problems. Okay, so good points of free boundary, and we will prove that at good points. When I'm saying good points here, this doesn't mean anything right now, but it means that that is not a cusp. If it's not a cusp, a good point is a point which the free boundary is not a cusp, and the free boundary is not the high energy, doesn't have this high energy value. Then you will be able to prove that actually the good points are locally Lipschitz graph. And that's a lot. All of a sudden you go from not being cusp being a Lipschitz. If it's not a cusp, it's going to be Lipschitz. And Lipschitz graph would be anything like this. But the next step would be to prove that this Lipschitz is actually C1. You can do it differently. You can do it either by boundary Harnack techniques, which is very simple, but then you have to learn that. Or you can do with the same technique that we are doing here, which I'm going to actually do that. I can prove that it's this Lipschitz norm actually, if it's Lipschitz something like that, that Lipschitz norm is getting better if you're getting in a smaller ball. And I can prove that Lipschitz norm becomes 0 in the asymptotics if you take a smaller and smaller ball and look at that. So Lipschitz norm becomes 0. What does it mean? It means that the boundary has to be C1. And this can be a good exercise for you. So this is an exercise at calculus level, calculus 1. So at calculus 1 level, you have a graph. So think of a graph. So calculus honor levels or honor class, so what's called. So if you have a graph, so it's exercise. So y f of x, that's just one variable, basically, over, let's say, minus 1, 1. It's a graph. F is Lipschitz. So how do you say a function is Lipschitz? We say the function is Lipschitz, its derivatives are bounded, basically, almost everywhere. F is Lipschitz, it means that f of x, x1 minus f of x2 is less than a constant x1 minus x2. And from here you can define Lipschitz norm. What is Lipschitz norm? So Lipschitz, we define it like this, C01. We call it C01, Lipschitz. What is Lipschitz norm? So how do you define Lipschitz norm? What you do is you divide the whole thing with x1 minus x2 and take the supremum of all possible x1 and x2 going around, but never being equal. x1 is never equal to x2, but it allows to come as close as possible. And then you take the supremum value of that. That will be your norm. So Lipschitz norm is supremum of f of x1 minus f of x2 divided by x1 minus x2 over all x1 not being x2. And now you see that you can actually interpret this geometrically. So this is the whole idea behind the techniques here. And this geometric interpretation of all these things that goes back to the George and Luis Caffarel has cleverly used that in pre-boundary techniques, actually. And then there's a geometric interpretation. With codes. I want you really to do this. If you do this, it's a calculus level, but still extremely advanced technique. So being Lipschitz, it means that at each point you have a cone from above and a cone from below. And the vertex of the cone is touching the boundary, the graph on each side. This is being Lipschitz. And you move this around and you will never see, so this sets never see the graph. Okay? It can be a free boundary or it can be just this one. So you move around, it will not be. At some places this can open a little bit larger, at some places it's forced to be a little bit closer, and then if the graph is C1, this is the polar radius R, center Z. Okay? If the graph is C1, it says that if you let R go to 0, smaller ball, the cone can be opened more. You can open the cone more. Because if I take this ball, then I can take much larger cone. And in the limit, R goes to 0, that cone can actually be flat, completely, like a plane. That's the limit. And that's exactly the Lipschitz norm. So locally, Lipschitz norms would be 0. The Lipschitz norm at the level of R, being going to 0, will be 0. That's being exactly C1. So you can play around with this. And that's what I'm going to use. So if you want to prove a graph is Lipschitz, and it has to be C1, how do you do that? You say that, okay, if I take that ball R, if I make it smaller, the norm will be smaller. So that Lipschitz norm C0, f of C01, that will be smaller and smaller if the balls are smaller. So it means that when you're looking at smaller in the scale to a polar radius 1, it's becoming more and more flat. In the limit, it will be completely a plane. Okay. Well, the good thing with this is we really have no other tools. It's just geometric thinking. It's just geometric thinking. And anybody who has calculus 1 should be able to do this. But then you really need to think deeply. There is a paper by Luis Caparelli from '77 in Acta Mathematica. And that paper actually contains all these geometric thinkings, and also later on, of course, papers that are coming up. But that paper, the particular paper, actually uses Harnack's inequality, maximum principle, and calculus. I don't remember anything else in that. So anyone who is taking a simple PD course should be able to read that paper. And that paper is the first paper in regularity theory. It's one of the best papers I've seen. But you have to rewrite it for yourself before you can really go through it. Because the notations are different from one page to another. All of a sudden they exchange to Z, they change to Y. But still quite readable. It's a very nice paper. It's one of the most beautiful papers I've seen. And everything is just calculus way, geometric and calculus way. Okay, so the Lipschitz points are C1, so you improve the norm, basically. Okay. Of course, you don't improve the norm at the large level. You have to go in smaller one, because it's not true. The Lipschitz norm completely, you're looking here, is not. Because the supreme we're taking, then there are cones that you cannot open more. So you take the balls smaller and smaller, and the cones become better and better. All right, so let's see what's going to happen with this. I think it was like, so the question is how to prove something is a graph even, not even smooth. Forget about smooth. Prove that the free boundary. You want to prove that the free boundary is a graph. Let's start thinking about that. Not even smoothness. A graph can be anything. So I want to prove that the free boundary locally. So if you come to the free boundary, look at it, and go closer, then there's a level that it looks like a graph. You can represent it by a graph. Not necessarily a smooth graph, but like a graph. And so how do you work with that? So of course you have to work with the function. There is no other way. The only thing you have is the function itself. And you have to work with the function. So how do we involve the function? Here's a particular example, which doesn't necessarily give you 1 here, but a little bit different. So if I look at this function, u of x, I'm taking a very specific example. You can think of this, let me just draw the picture for you. So whatever I'm going to do today and tomorrow, it's in this example. So we have to make this example to work as at the technical level and at the general level. Okay, so let me open it. So let's first look at this, see what it is. So this is a function, if I can draw it correctly. So I have in one dimension, x1, I'm having my next direction, x2. Why do I choose it like this? I'm choosing this, I'm looking at x2 minus this guy, and then plus. So this will be, if you look at x2 minus cosine, if I just want to draw this picture, it is 0. x2 minus cosine being 0. So that's, cosine is this, yeah? And then you have an m there, so it means that it oscillates fast. And then I have moved it up with 1, so it doesn't go below 0. Okay, there's an oscillating graph like this. Am I right? Is that picture?
It's negative. I mean, it's other upside down.
Is it upside down?
With minus cosine, that's what. So
When x1 is 0, what happens?
it's minus 1 plus 1.
x1 is 0, cosine is, yeah, x2 is going to be 0, yes. So it's upside down, thank you. Yeah. So this is the liver picture, so we get, that's the correct picture, yeah? Am I right just now? Anyway, some picture like this. I think I did it so I can take the origin as a point. And I'm taking this to be positive, so that will be positive here. So that's set when u is positive. And u is going to be 0 here. Now you realize that if I take Laplacian, it will be m squared, something, some f of x, which I don't care. It's a smooth function or something like that. And if you look in this direction, Laplacian of u is exactly some constant, some function times characteristics, like the obstacle problem. It actually solves an obstacle problem with this density. So this is an example of an obstacle solution to an obstacle problem. Locally, if you take boundary values according to the function u and the Gola rate is 1, and if you put this whole guy here as your density when you're minimizing, so that would play the role of f in the original setting, then you will actually have this example. Specific example. This function is a graph in this direction. Agree? Well, the free boundary is a graph in this direction. The free boundary is also a graph in a little bit tilted directions. So in all these directions, it's going to be a free boundary. You cannot say that it's a graph in all directions. So Lipschitz norm here is actually very high if you stay globally. And then it becomes worse. If you let m go large, it oscillates faster, and free boundary is still C1, but it becomes a little bit worse. So C1 norm becomes worse. So this is a good example. Now, let's say we have this example, we see the picture, and I want to prove that this is a graph. So what can I do? Here is the game. Okay, here's the game. Take any vector, E, and that vector is approximately E2, so this is E2 vector, this is E2. So take anything very close to E2, not too far from that. In order to prove that this is a graph, we need to prove, since the function u is non-negative, it becomes 0 on the free boundary, then it's enough to prove that dEu is non-negative. If the function dEu is non-negative, what does it mean? It means that if you go in the direction E, the function is 0. We know it's 0. Here, according to the picture, it's 0. And then you go in this direction, it becomes all of a sudden, so you hit the free boundary and then it becomes non-negative. Because the function, this is saying that dEu is going to be non-negative. So it means the function is increasing. In all these directions, increasing. So if you want to prove that this graph you have, or this level set you have is a graph, what you prove is that your function is increasing in that direction. Think of a level surface. If you want to prove locally that level surface is a graph, it's enough to prove that there is a direction, there is a normal direction, and you can find it. Of course, it might be 0, but let's say it's strictly positive just for making the case. If it's strictly positive, it means it hits 0, then it becomes positive. Of course, it's going to be 0 here, so we cannot say it's strictly positive. So in these directions, any directions E, which is very close to E2, my function is increasing. And then this E can be anything close to E2. So in higher dimension, it can be a cone. And that means that I have that cone. Function is non-negative in this cone, 0 in this cone. And then I can put this point a little bit around it. That's it. I'm done. That tells me that the free boundary is Lipschitz. So can I do this technically, at the technical level, without seeing the picture of my free boundary? Okay, this is a computation. I would like you to verify these computations. This is just by hand, in this particular example, of course. And this is what I'm going to do, actually. I'm going to try to verify these things.
So basically, if we would want to show the boundary is Lipschitz, say we first find one direction
Yes.
from which it is not 0,
Exactly.
and then try to find a neighborhood of that particular direction.
Well, exactly. Neighborhood of that direction, that's correct. So you find the direction,
and then
suppose you blow it up, scale, blow it up, it becomes a plane. Then you know that there is a direction. You choose that direction with a clever way to say that, okay, in this direction, and anything close to that is going to be monotone increasing. And that means that in any direction around this is going to be, free boundary is going to be, you're going to have codes. But of course, also these points are the same. You go in this direction, these points also graph, and then a little bit tilt, and then also here. So you get actually the whole free boundary in that smaller ball is going to be a graph, a Lipschitz graph. That's exactly the way you have to do it. Well, not only the way, but this is one of the ways at least. And we have that in this particular case, by computations, we actually get this. The question is whether I can get this guy here. So how do I work with the function? It seems that working only with this function is not enough. You need a little bit more. And that would be this one. So the suggestion is, instead of working only with dEu, if I go back here, you see dEu minus this guy. Forget about that, this is larger than or equal to 0. This is good for this example, because I can see that. Well, I see it in anyway, everywhere. But let's say I want to prove this one. Let's do it here. I want to prove that dEu is larger than this guy. If I prove that, then this is larger than or equal to 0 and that. So let's prove that dEu is larger than this. It means that we want to prove dEu minus some constant u is larger than or equal to 0. So let's prove this. If we prove this, then you take this on this side and you get dEu is non-negative. So how to prove that this is non-negative? So this means that this is a program. This is a good suggestion. Might not work. We don't know. If you do as a researcher first time, you don't know. You just play around. You have all the possibilities, exhausting them, trying to see what's going to work for you. And this is one way of thinking. This actually came much later than the original proof. It came in 98 in Luis Cafarelli's paper, which actually simplified the proof very much. So the original proof is much more complicated. Doesn't use any tools, but it's more complicated. So we will actually play with this. And now, what we will be using, if you remember, which you probably don't, because most of us probably don't, is that I told you about this non-degeneracy lemma, the device. Said that I'm going to use that again somewhat differently. That's what we're going to use. Because if this is harmonic, the derivative is a harmonic function. Because Laplacian of u is 1, so Laplacian of du is going to be 0. So it's harmonic inside the domain. And Laplacian of this guy u is minus 1, so it's minus 1. So I need this x to power 2 to sort of compensate that. And I'm going to break it in. So let's take a break, yeah? So take a break.
No, I asked him to come at 11 o'clock.
Okay, then I will continue. I thought it was a good place for break, but okay. So let's go on with the. Okay, so we leave it there. We will be back to this. So we need a little bit of tools before we go and use that. Okay, so scaling and blow up. You have seen a little bit about this. So let me go a little bit into it, further into it. So if you want to study this is your free boundary. The picture is much more nasty. So what you do, you take a point and you look at point, because you cannot prove that your free boundary is not monotone in this direction. But if you go here, then it's going to be monotone. So you have to go into smaller balls in order to, for you to be able to see the monotonicity, the directional monotonicity. You have to go in a smaller ball. Okay? Well, what I mean is that let's say, I mean, you cannot claim that this is monotone in this direction. There's not a graph in this direction. So this is the free boundary point. And then you say, well, if I go here, forget about this large ball, here, then it's going to be a lot of directions. And if I go even smaller, just make the picture larger, it's going to be, so there's going to be lots of directions. It's not necessarily so, it's going to be maybe in other directions. So I have to go smaller and smaller, into smaller and smaller ball. And when you go into smaller and smaller ball, this is exactly what you're doing. Or this is how you should be doing. Because you only have the function. So you scale your function at the point z, you zoom it, and the solution will now be going from b1 to b of 1 over r, much larger ball. As r goes to 0, 1 over r goes to infinity, you have a solution in complete space. The PDE will change accordingly. Okay, there will be a scaling. So if you take Laplacian of this, r squared kills this, it will be Laplacian of u at the point rx plus z. And this is just rewriting of that. You also know that this function, if you remember, we said that u, supremum of u over ball of radius r, if this is r here, it will be less than c1 r squared, and larger than c0 r squared. But since I'm dividing with r2, it will be less than c1 and larger than c0. So this tells me that my function doesn't flat out and it's universally bounded on the ball of radius 1. And you actually get boundedness at any level of r, capital R. Whatever big R you take, capital R you take, it's still will be bounded. There will be r squared here. If you put a capital R here, it will be capital R squared. And the scaling will be pictures like this. Have you tried to do geometric scaling of a graph of a set? So you want to scale something at the point z. So what you do, you translate this to the origin. You translate the point to the origin and then scale it. That's exactly the translation. So I'm transferring the whole thing, translating the whole thing. Instead of Z, I'm now changing the whole domain and then scale. So that's the scaled version. These are all geometric play around, so you have to do this in your off time. I think these are things that are maybe not coming natural to master and PhD students if they don't work specifically with this type of problems. So what happens next is that when R goes to 0, the solution goes to some limit by compactness. And of course not for the whole sequence, for a subsequence. That's the trouble here also. But you overcome that. So you blow it up and you know that there is a subsequence. Let's say Arzela-Ascoli for simplicity. So by compactness, there is a subsequence which converts in entire space, on any compact set of the space or an entire space, to a limit function, and the limit function will still satisfy the same PDE. And maybe we can take this as an exercise part to prove that that limit actually is going to get the same PDE. So in the previous page you had this. Prove that this, along with this guys here, give you convergence of the PDE, of the solution you are, or the PDE actually, to the same PDE. So you can put it as an exercise. And moreover, we have this one. This is not mentioned that much here, but we know that this guy is universally C11. So U is universally C11. So I will probably ask you as an exercise to prove this too. So prove it's actually going to be bounded by R squared for any R. And that tells me that this is very important. This is one of the keystones. So you have to really prove this. It's going to be used. I think I'm doing it, so this will not be an exercise. Yeah, I think I'm doing it here. I didn't forget that I was doing it here. That's a good exercise. You want to add it? Okay. But try to verify it for yourself. So what you do, you take your 0x is approximately like this guy for the subsequence. So Rj is the subsequence now. And I can take x to be something very large, like Ry. And y is like Borel rate is 1 or something. And then I can rewrite it. I can put an R here. I just put an R here and an R here, so they compensate each other. So dividing and multiplying. But then I know that my function is C11, so this is completely bounded. This is what we prove, that this is bounded. If this is bounded by a constant, then I'm going to get R. So it means that my function, when I'm scaling it and blowing it up, it will be behaving like R squared at infinity, at most. It's always below this parabola of R squared parabola like this. And that will be useful for us. We're going to use that when we're using, I'm going to apply a few different devices, and I will need that. So my second derivatives are universally bounded in entire space, and that's good. I'm going to use monotonicity formulas of different type also, and I will need that my function is quadratic at most, so I can control them at infinity from the values of this function. So what happens if you want to look at this problem now, at this setting? It means that if you want to study the free boundary at one particular point and close to that, in the vicinity of that, you zoom it. If the zooming gives you something very bad, zooming usually improves things. Agree? If you zoom it, it should be better. Hopefully better. But if you zoom and zoom and zoom, it's always bad, and even in the limit it's bad. So how can you hope that the original version was good? So think of cones. If you zoom a cone, it will always stay a cone. It will not get better. Let's say the best things, the best surfaces we know are flat surfaces, planes. These are the best ones. If somebody asks you what is the best surface you know, you would say an affine plane, okay, an affine graph. So if you have something like this, that is your graph, let's say, or your set, then you will say that this set is nice because if I take any point here, there is a tangent plane. If I zoom, to take a small ball around it, VR, and Z, and zoom it, then you will have a picture which is like this. In the ball of radius. And you let R go to 0, this will be a plane. So it improves. So a good point will improve. The graph of the graph around a good point will improve. But if the graph is not improving, if there is a cone here, so if there is a cone and you zoom it, it will be this picture. And this is not a good graph for us. So it means if the limit one is not good one, which has to be better than the original before zooming, so the unzoomed one cannot be a good one. Okay? Or alternatively, if you have, so here, let's say here is positive here, and here is positive here, U0 is positive here. So an alternative is also that if the graph is something like this, the cusp, if you zoom it, it will be something like this, and maybe something else will come along. Here is positive here is positive here, and then you see that this graph, I'm just doing it the picture, but this will be U0 sort of. Actually, U0 will also be 0 here. It just comes in because it goes faster in that direction to 0. So quadratic scaling makes it 0. Okay, this is a graph, sort of, but think in dimension 3. This might not be a graph. It might be just a line. So generally, these are not good points for us. So the good point is when this positive, U0 is positive on one side, and U0 is 0 on the other side. Because then I can use this DEU0 being non-negative. Because in this case, DEU0 is not non-negative. If you take in this direction, it will be positive here and negative here. So this is not going to work for us. So we need that really it's 0 on one side. Yeah, so we need that it's positive and then 0 on the other side. Then this is, at least, it's a good chance of giving us regularity. We don't know that yet. So here are a few pictures. So this is kind of Casimir type. Singularities can happen. If you zoom in at this point, the picture will be this. You zoom further, it will be something like this. You zoom further, and then the limit. So that's a cusp point. We don't like these cusp points. So we'll try to avoid. So what we need is a mechanism to say that this is a cusp point and this is not a cusp point. And with that mechanism, I can say this is not a cusp point. If I can see that it's not a cusp point, then my statement would be that this is going to be a C1 graph locally. So you see, this is a very strong result. If you don't have cusp, if the point is not cusp, it's going to be C1 locally. So global pictures are very important as the blowups. So what we have to do is that we have to go and look at the global pictures. Because if we get a sort of hint from the global picture is good, then I have a chance to go back. But how we go back and how we use that, that's a different story. But at least we have to look at the global pictures. So it means that when you zoom and you get something global, you have to now forget about your original problem, and you're here with global solutions. How can a global solution look like? So we have to classify them. Look at all possible global solutions or blow-up solutions. So if you want to do a simple proof, we will look at blow-ups. It means that everything is coming from one function. Then I use what's called uniformity, because I want to say something like this. If it's not a cusp point, then it's going to be regular, and the norm depends on the ingredients. But that requires that every time you change your functions, because you say that the norms might oscillate. It's not the same function, but the norms are always within a limit, but the function is changing because you want to make something uniform. And that's a very much harder theory. So we're not going to do that. We're going to stick to only blowups. That's one function. So classification of global solutions is a little bit harder, generally. So we're going to stick to the only blowups. And that will give me just C1, but not uniform C1, which is, I think, reasonably good. The next stage will be a little bit harder. Okay. Now, you realize from the pictures I was drawing for you, I was always drawing homogeneous cone type, yeah? Everything was like a homogeneous cone thing. Open cones, closed cones, and all possible type of cones. So cones are homogeneous domains, basically homogeneous sets. And that's actually correct thinking. So when you blow up something, so you're sending, it's like rays, you're sending them out, and you see that the limits will be independent in this direction. It's going to be cool. So what you're doing, you're sending everything that is even coming close to this to infinity. Everything that's even close. So all information is coming only from this point. That's a strange way. But when you do this zooming, the only information, wherever you have on the ray, is coming from this center. So try to do this with pictures, graphs, or whatever you have. So if you would look at this example, so let me do a few examples so we can see that. So if you look at the picture, if you look at this picture, let's take something like this. I have to draw it the other day for you. Okay, so this is the point, and then you can have something coming here, making a little bit curve. Can you see that, or it's too? So if you zoom this, you see here I have something very flat, but you have to go extremely close to that to see that flatness. So when you zoom this picture, everything disappears. Everything that is not flat, sort of in this direction, will disappear. And it will become, so the picture here will become a limit, something like this. And now, if I take another picture for you, okay. Now I'm going orthogonal to this. I'm going this direction. And now you can put anything you want to. Doesn't really matter. let's take that, you take even a sequence that is not, so for any R, that set is outside R. So if you do that, then you will see that everything will disappear in the limit. If you scale this, the scaling will be this direction survives because it goes all the way down, this direction survives, and this direction survives. Now let me give you another picture which is more interesting, and that's the trouble point. So if I have a picture like this, here is my free boundary. So suppose my free boundary looks like this. It goes like this here, it goes like this here, and then it goes, let me see, it goes like this here, it goes like this here, then it goes like this here, it goes like this. Okay, and it continues. Like sine function, sine over 1x here, and sine over 1x here, something like that, with one side and two sides, doesn't really matter. So if you scale this at these levels, so they are like this. If I scale it at this level, and then next one is this one, at this level, what you're going to get is this. Okay, and you scale it, next time you're going to get something even smaller, something like this, in the limit of this one. If you scale it at the, which level did I say? If you scale it, I would probably have taken this level, yeah. If you scale it at this level, so this guy survives, the picture will be what? The picture will be something like this. Next time, it will be something like this. So the limit will be this one for that sequence, for the subsequence, and the limit will be this one for the other subsequence. So you see the difficulty. The limit is not necessarily unique. It might be all possible things. So we are looking for having a direction when the function is going to be like a plane in this direction. And now all of a sudden I might have several directions. So how do I cope with that? But now think like this. If I'm able to prove that for some RG level, I can prove that my function is going to be monotone in this direction. If I can do that, that it means that this doesn't happen. It cannot happen. So I really don't need to think about it, but that's a possibility that can happen. But if my device doesn't see that, doesn't care about this, then I'm fine with that. So my device here, I'm going to show you, which actually appeared in the 98 paper of Luis Caparelli. This was a very beautiful device. We will then later on using this very strongly. That device tells you, I don't care how it looks. As long as it looks like almost like a plane at one level, then I can prove that in a smaller ball, it's like ellipsis graph. Then it cannot oscillate and be a different thing in some other directions. Okay, so what we have to work with is homogeneity of global solutions. If I can prove that global solutions are homogeneous, the blowout solutions are homogeneous, blowouts are not necessarily homogeneous, but blowouts are homogeneous, it means I can take one of the sequences and just work with that. And once I have classified homogeneous global solutions, because I don't know yet, I'm just showing you good pictures. I don't know yet a global solution, how it looks like, or a blow-up solution, how it looks like. So first we prove little bit properties, and then we classify the blow-up solutions. That already is a whole machinery. You have to classify that. So I will give you the following question, not specifically that you would need to do it, but this is the question you're asking us. Suppose we have this solution in entire space, and suppose U0 is a blow-up solution. How does it look like? If U0 is a blow-up solution, and it solves this PDE, then I will claim that it's either a polynomial, so U0 is either polynomial, then I know exactly how it looks like, or U0 is what we call half-space solution. It's like one-dimensional solution. And one dimensional is like x1 to power 2 in this, divided by 2, and then 0.
So there will not be any right hand side, or it will be there, even there, strictly.
Here.
So in entire Rn, the right hand side is still characteristic function of Euclid.
Yes. Everything disappears. If there is any ingredients, it will disappear. There are functions, they will all be constant because you're scaling them. It will take continuous functions. If you scale them, it will be exactly the value at the point, unless you divide it. Okay, so we need to classify global or unique in this particular case. For a talk here is homogeneous. Blow-up solutions. And I'm claiming that blow-up solutions are going to be homogeneous, and we will prove this. Once we prove that, then it's easier to prove how they look like. So I think we can take a break now, and we come back to this very soon.